Hi and welcome back to video 8.2. Today we'll be covering Bronsted-Lowry theory. This is going to be the second part of our acid and base PowerPoint. So by the end of this video, you should be able to recognize strong acids and bases versus weak acids and bases. You should also be able to identify acids and bases using the Bronsted-Lowry theory. And lastly, you also must be able to identify conjugate acids and bases. So what is a strong acid? A strong acid is going to be an acid that's going to ionize 100% in water. And so over here, you're going to see S electrolyte. This just means that if there's 100% ionization in water, meaning that it dissociates, this just means that you're also going to be a strong electrolyte. Now, there are 7 strong acids that you need to know by heart. And so I have this little mnemonic for you guys. The first thing you need to know is that there's something called binary acids. A binary acid is when there's only 2 elements. So the first element is always going to be hydrogen. So here we have Hi, and if you look at that, my mnemonic right there, it says I bring clay. Those are going to represent your gases that we need you to know. So I represents iodine, bring represents Br from bromine, so your next one's going to be HBr. Now this is still just 2 elements because hydrogen is its own element and bromine is its own element. This Cl is going to represent chlorine, so the next one's going to be HCl. So then you have hydrochloric acid. Now remember, by now you are expected to know how to name these: hydroiodic, hydrobromic, and hydrochloric acid. Okay, so the next group of strong acids that we have are what we call ternary acids. Now a ternary acid is when you have 3 or more elements put together. Now your first element, once again, will always be hydrogen, and your last one is always going to have an oxygen in there. So when you look at these, you're going to see nitric acid. Notice we have our hydrogen, we have our oxygen. So we're going to ask ourselves this: if you take the number of oxygens, which is 3, and you subtract it from the number of hydrogens, which is 1, is it 2 or more? And in this case it is, so this is why it's a strong acid. 3 minus 1 is 2. All right, our next one is chloric acid, and 3 minus 1 is also going to be 2, so that's why it's strong. Followed by perchloric acid. 4 minus 1 is 3. And then our last one, I know you can't see it, but it's sulfuric acid, and this is going to be H2SO4, so 4 minus 2 is 2. So these are going to be all your strong acids. You do need to know these by memorization, but remember, it's not like you need to know nitric acid. You just need to know, hey, if there's 2 more O's than hydrogens, then it's going to be strong. So make sure that you understand the rules as opposed to just memorizing, okay? So I bring clay, 2 or more O's than H's. All right, so I just want to show you guys an arrow, what the arrows represent over here. I haven't talked about this in the past, but I'm going to fill it in now. Whenever you see a single arrow like this, this represents that you have 100% ionization. So in this case, we're going to say that this is going to be a strong acid. So a single arrow will represent a strong acid or 100% ionization if there's no acid involved in the reaction. So often we write HCl as HCl, you're just simply going to ionize it, meaning you don't need to necessarily throw it in water, because water, we're under the impression that we always just throw things in water to see if it separates into its ions. You don't have to do it. You don't have to put H2O, but if that helps you, then you're more than welcome to use that, or you can just separate it. Either way, you get the same thing. All right, because remember, H3O plus is the same thing as H plus. So it's the same exact. And we'll talk more about that moving forward. So if that didn't make sense to you yet, I think by the end of this PowerPoint, it's going to stick. All right, so these rules over here, or I should say the ternary rules over here, all of these are going to be your strong acids, but there is an exception to that. There's going to be times where you're going to have a carbon involved in it. So in this case, we have a carbon. Anytime you have a ternary acid and you see a carbon, and I'm saying a carbon, like a carbon by itself. I'm not saying like a Cl, because Cl, this is chlorine. This is not carbon. This is chlorine. So be careful. Whenever you see a carbon in itself within the compound, this is going to indicate that it's no longer going to be strong. By default, it will always be a weak acid. So this rule will oversee the rule over here. So be careful with that. All right. So going back to that previous rule, another thing that you got to watch out for is that the 2 or more O's than H's represents the parent function. So the parent function is going to be your compound that does not have a charge attached to it. So if I go back really quick, you're going to see that all of these have no charges on it, you see? So these would all be examples of parent functions, but let me show you what's not a parent function. If you see H3PO4, we say that he's the parent function of this guy. Now, how do we know that? Well, notice we have the same elements involved, but this guy has a charge in there. So whenever you see a charge, you know that you have to base that previous rule, the 2 or more O's and H's, off of the parent function. So in this case, you say, is there 2 or more O's and H's? And you would say, yes, there is. But remember, that rule, 2 or more O's and H's, only applies to the parent function. And if the parent is weak, then all his little derivatives will also be weak. So yes, there is 2 more O's and H's, but remember, he's not the parent. So by default, we're looking at this guy. So we're asking ourselves, does he have 2 or more O's and H's? And if he's not strong, then son, daughter will not be strong as well. So hopefully that makes sense. Look, and I'm going to be honest with you guys, at this level, this isn't super important to understand, but if you're in the AP classes, yes, you need to know this. This is something that you will be asked. They love to throw you these trick questions, so make sure you know this by heart. Or if you plan on taking AP, make sure you know this by heart. Let's talk about the weak acids. The weak acids are basically everything else, or they contain carbon in there, right? And anytime you have carbon in it, we basically consider that an organic compound, because carbon is basically organic, right? That's something that is spread throughout life. Now, weak acids, there's only going to be a small dissociation, so we are no longer at that 100% dissociation like in that previous one. But more importantly, look at this arrow that we have over here. This is a double-sided arrow. So whenever you have a double-sided arrow, this means that you have a weak acid. Now, what this is really trying to tell you is that the concentration over here can shift back to this direction, and the concentration over here can shift back to this direction. So basically, they're constantly moving back and forth, and they're kind of in this balanced state. When you have that single arrow, it's basically saying, no, all the reactants are going to completely transfer over to the product side. There is no going back. So that is really the difference between the two. But let's move forward. And this is what I was talking about right here. I just mentioned this. So this is what it's trying to tell you about. The products can go back to reactants, and reactants can go to products back and forth. All right, let's talk about the dissociation of strong and weak acids. Just pay attention to the arrows. You're expected to do this, so just make sure you know how to do this. HI, well, if you were to just dissociate it, right, it's going to separate into H plus and I minus. But the question is do you have a single arrow or a double-sided arrow? Now remember, this is a binary compound, so this is going to be a single arrow, right? Same thing as this one. If you look at this guy right here, this is an acid. We know it's an acid because it has that hydrogen in front. Same for all of these. These are all acids, right? They all have that hydrogen. But more importantly, as you keep paying attention, you're going to see that there's a carbon in there. And automatically, if there's a carbon in there, we can say that it's weak. So we should see a double-sided arrow like that, right? And don't forget to put the charges, guys. That's one thing that students miss. They get the question wrong because they forget their charges. So make sure the charges are constantly getting you to 0, right? +1 minus 1 is 0. +1 minus 1 is 0. In this case, H2O. H2O is coming from that last PowerPoint. It's both an acid and a base. In this case, we're going to look at it as an acid. But when you separate this, you should know that water, think about it. If you drink water, does it burn your throat? Does it taste sour or bitter? And the answer is no, right? It's no to all of those. So you know that this is just going to be this is going to be a weak acid or a weak base. It's not strong. Okay, so we see that double-sided arrow again. All right, so you have to know your strong bases too. These you do need to memorize, but once again, I got a little trick for you guys that hopefully it makes it easier for you. So when we go through this is what you need to know, and I just want to cover the trick for you guys. I think that's going to make it a lot easier instead of having to go through all these steps. But there's really just 8 strong bases, and the 8 strong bases makes a B on the periodic table. So if you look at it right here, you're going to see it's going to be lithium to cesium, and then back from barium to calcium. And notice it makes this little B. You got to use your imagination a little bit. And honestly, I didn't put these lines as straight as possible. I could have made it a little bit prettier, I'm sorry. But just picture this nice little baby B here. And those are going to be your strong bases, okay? So basically, it's your group 1A elements, and then you're going to have barium back up to calcium. All right, so just be careful there. We love to, there's all type of questions we like to ask, knowing your strong bases and weak bases. So just know that there's 8 of them. Okay, and I should also tell you guys that your strong bases will always have hydroxide in there, and that's simply because, well, hydroxide is base. Remember, hydroxide from that first PowerPoint is a base. So you should also know, because it's a base and it's strong, you're going to have that single arrow again. Okay. So let's look at our weak bases. Our weak bases don't completely ionize in water or dissociate it. These are going to be your weak electrolytes as well. Now, one thing you need to know about your weak bases is that they're always going to contain the nitrogenous base, which is your NH base. So if you look at my examples over here, I got CH3 and NH. NH is automatically telling you that this entire molecule is going to be a weak base. And then we look at it over again, over here, NH3, which is ammonia. Because it's that NH group family, we can also assume that this is going to be a weak base. So basically, anytime you see anything with NH in the end, or NH whatever, you're going to have a weak base. Okay, so these will always have those double-sided arrows. All right, so let's move on to our definition 2. Our definition 2 is our Bronsted-Lowry definition of acids and bases. And this is really where I want to pick up, but I needed to give you that background first. So whenever we're talking about the Bronsted-Lowry definition of acids and bases, acids are just going to be your proton donors, while your bases are going to be your proton acceptors. So if you're an acid, you have an extra hydrogen, and you're willing to give them up. All right, so acids give up protons, which is just going to be your H+, right? So here's a little picture I have for you guys. I thought it was kind of cute, and I thought I'd share it. It says here we have a proton. This is the acid, right? And you can see that he's giving them to the base because this guy's saying, gee, thanks. You know, so I just thought that was kind of funny. But okay, let's get back to this. A proton is just a hydrogen atom, right? A proton is just a hydrogen atom that has lost its electron. And that makes sense because this is why it's positive, because there's no electron, which leaves you with that positive 1 charge. All right, so we can easily demonstrate acid and base reactions by throwing it in water. You don't have to throw it in water when you're talking about the Bronsted-Lowry definitions, because you're just going to say, hey, does it donate a proton? Yes or no, and that's going to dictate whether it's an acid or basis. So that is the difference between a Bronsted-Lowry and an Arrhenius definition of an acid. Remember, the Arrhenius definitions is you need to throw it in water and separate it, and if it separates into H+, it's going to be an Arrhenius acid. So if you form H+, it's an Arrhenius acid. And in this case, the Bronsted-Lowry definitions, you don't necessarily form an H+, right? It's just going to be whoever donates that H+ proton is the acid. All right, and let me show you what I mean. Let's go to this next step. Let's look at these examples, because definitions are always like, what? So let's just look at some examples, okay? So if you see this example over here, what I'm trying to say is this HCl and this H2O. What you're going to ask yourself is this question. Hey, in order for HCl to become Cl, what must it have done? So what must this guy do in order to become this guy? And so hopefully you're saying, well, HCl must donate a hydrogen, right? He must get rid of a hydrogen. And if HCl is getting rid of the hydrogen, that's going to make him the proton donor. Remember, our last definition tells us if you're a proton donor, you're going to be the acid. So he's the acid. So by default, whenever you know your acid, the one right next to it will always be your base. All right? So because he's the acid, he's the base. Now, the way you're going to group these up is once you know your acid, you by default know your base. But you also know that if you compare, you're going to compare this HCl to whoever looks like him the most. In this case, it's Cl minus, right? And when you compare the two, he's the acid. His base pair is going to be the conjugate base. So acid, conjugate, base. Now, this is the base. His base pair would be the opposite. His base pair is going to be the conjugate acid. All right. So let's look at the rules. Here are the rules. I have them all written down for you guys, and it's exactly what I just said. So I'm not going to repeat it, but let's just look at this next problem right here. If you look at HNO2, right, we're going to compare it to the right side. And if you compare it to the right side, what must nitric acid do? I'm sorry, nitrous acid. This is nitrous acid. What must nitrous acid do in order to become NO2 minus over here? Well, he must lose that hydrogen. So when he loses this hydrogen, this makes him the acid by default. This makes him the conjugate base, because remember, his base pair over here is always going to be the opposite. So once we know he's the acid, we also know that he must be the base. And because he's the base, his opposite pair must be the conjugate acid. All right, so just remember, the acid-base pair is only different by one hydrogen. So once you know the hydrogen, just get rid of one hydrogen, and that's going to be his conjugate. I want you guys to try these by yourself, and if you can't do it yet, that's okay. Just watch this video. Let's talk about it. I wrote down the steps for you guys here so that you guys can see them. But once again, you know that NH3, in order for NH3 to become NH4, in this case, we're doing the opposite. Here we must gain a hydrogen, right? We must gain a hydrogen. So if we're gaining a hydrogen, this is going to be the base, right? This is going to be my base. By default, this must be my acid, all right? And we also know that if he's the base, his base pair is going to be the opposite of him. So if he's the base, he must be the conjugate acid. All right. If he's the acid, then his base pair must be the conjugate base, right? So I'm really hoping this is starting to make sense to you guys. And if not, this is kind of one of those units where you might need to watch the video once or twice. It is conceptual, but you will get it. If you stick with it, you are going to get it. Okay, so I want you guys to try this one by yourself as well. You might find it easier. Here's just a useful hint for you guys. Sometimes it's easier just to focus on the ending so you can see who goes grouped with who. So what I'm trying to say is, and pause this video if you want to try it by yourself, but what I'm trying to say is look at CL. You're going to find his partner. His partner is CL over here, right? So I'm saying focus on the endings. So if you see CL here, you know that his partner is over here. So you would draw that little imaginary arrow going like that. And you're going to ask yourself, what must hydrochloric acid do to become potassium chloride? Well, he must lose a hydrogen, right? We're just focusing on the hydrogens. We don't care what the heck happened with the K. We just care what happened to the hydrogen. Well, we lost it. Now, if we lose it, that's going to make him the acid, right? So he's the acid. And if we know that he's the acid, we know that by default, his partner over here is going to be the conjugate base, but we also know that this guy must be the base as well, right? So he's the acid, he's the base. If we know that he's the base, his partner that he's connected to is going to be the conjugate acid, right? Because they're opposites, right? And so that's all I'm trying to say. So it's really not difficult. I think once you start practicing these, you're like, oh, this is easy. And you're like, yeah. But the hardest thing, I'm telling you, the hardest thing right now at this point is going to be, can you identify the partners? And once you're able to get past that, I think it's going to make a lot of sense. All right, so let's try this one. All right, so you're going to take Na2CO3. And when you compare sodium carbonate to hydrochloric acid over here, what you're going to do, you're not going to compare the two to each other, but you're going to find CO3 and find them on the product side. And once you see them on the product side, all you're going to have to do is ask yourself, what happened? And notice there's not a hydrogen over here, but there is a hydrogen over here. So what did this guy have to do in order to get this? Well, he's going to be receiving an acid, right? So this makes him the base. He must receive an H+. All right, so he's going to be the base. And if that didn't make sense, it's okay, because you should know. Let's look at HCl. All right, what must he do in order to become NaCl? Well, he must lose a hydrogen. Remember, we don't care about the sodium. He must lose a hydrogen in order to become NaCl. So you should know by default, he's also a strong acid. He's a strong binary acid. So you should just know off your head that this was your acid to begin with, right? So he's the acid. Now, once you know the base and once you know the acid, you know that their base pairs are just the opposite. So if he's the base, that makes him by default the conjugate acid. And that makes him the conjugate base, right? So super straightforward, guys. I don't want to waste your time with this next one, but I do have the answers here for you right here. So you're more than welcome to just pause the video, take a look at that one, see if that makes sense to you guys right there on why it is the way it is here. And just remember, guys, there's going to be times where you might be confused, but if you understand the other definitions of strong acids and strong bases and your weak acids and weak bases, you can kind of cheat a little bit and say, hey, NH3 is always going to be a weak base. By default, you know he's the base, right? You know he's a nitrogenous base, so you already know that he was the base to begin with. You could do the same thing for HCl. You know that potassium hydroxide was part of the 8 strong bases, so by default, you should have known he was a strong base. You should have known that this is a binary strong acid, so you can kind of cheat your way through this if you needed to. So, and it's not really cheating, it's just that you really understand your strong acids and strong bases, and that gives you an advantage here to just like breeze through this. What I'm saying is you don't even need to look at the products if you understand your bases and acids, right? All right, so let's talk about amphoteric substances. An amphoteric substance is something that acts as both an acid and a base. So it can be both, right? And we talked about some of these in the past. We said that, hey, water is HOH, right? Which is H2O, which is HOH. So it has a hydrogen in front to get rid of, and it has an OH in the end to get rid of as well, right? So, and I don't want to say get rid of, but it ionizes into those molecules. So let's look at some other amphoteric molecules that we have here. All right, the first one that we have is going to be HCO3. Okay, so we have CO3, we have SO4, and we have H2O, right? So what I really want you to pay attention to here is that what makes them amphoteric is that they have a hydrogen that they're willing to give up. They can give up a hydrogen, right? And if you give up a hydrogen, you're now going to get CO3 2 minus, right? Because a hydrogen is a positively charged particle. So if you get rid of one positively charged particle, that makes this guy -2, right? So we get CO3 2 minus, but you could have also said, hey, why did you give up the hydrogen? Can't you also accept another hydrogen? You see how it's a negative charge here? Couldn't you say that you want to gain one more positive so that you can get rid of the charge altogether? And the answer is absolutely. You could have absolutely done that. And if you did that, you would have got H2CO3. Now notice this one has no charge. So that's really what amphoteric is. You have the option to either lose or gain a proton. And we could do the same thing for HSO4 and H2O, but I'm not going to do that. But hopefully this makes sense to you guys. So when you look at HCl plus H2O, the reason why this is here is because water is an amphoteric molecule. But in this specific problem, water is acting as your base. So I'll probably go back and add in another problem where water is actually going to be working as your acid, just so you can kind of see the difference between the two. But that's all that's really going on here, guys. Amphoteric means you can be an acid or base. How do you know? Well, focus on the charge, focus on if there's a hydrogen. All right, and if you have a charge, you can gain a hydrogen to offset it. If you have a hydrogen, you can lose the hydrogen, and then you get another, you're going to add to that charge another negative value, right? So let's create some conjugate bases ourselves. So let's take a second and let's go ahead and practice these ourselves. Remember, here's a neat little trick you guys are going to do. If you ever have a molecule that has a nitrogenous base in the end, that means that you're going to have a hydrogen there, right? And if you have a hydrogen in the end and you know it's a base, you're automatically going to lose from the base. You're going to lose a hydrogen from that base. All right, and so I have an example for you guys here. And I'm going to stress this right here. It's in bold because, look, I'm telling you, on your homework, after this quiz that I have, there's going to be a problem that's going to be looking very similar to this. So be on the watch. Watch out for that, okay? It is tricky. This assignment that I did post, it is very tricky. The questions, I don't know if you noticed, but I'm trying to put questions in there that you can't Google, right? I'm creating these questions, so it is difficult to try and Google them. And I'm telling you, as soon as I make the question, I type it in Google myself and I see if it pops out. And if it doesn't, I'm like ka-ching, and I add it into my quiz. So just know, make sure that you truly understand these videos. All right, so let's look at H2PO4. All right, so what we want to do is we want to create a base. Remember, a base is just going to be that you're going to be losing, you're going to have one less hydrogen, right? So if you look at H2PO4, your conjugate base is going to be HPO4 -2, right? Remember, so a base, a conjugate base is simply just one less hydrogen than what's there. All right, so if you look at HClO2, well, we're just going to remove that hydrogen and we get ClO2 minus, right? If we have OH, we're going to get this. This is kind of tricky. This is why I kind of like stuttered a little bit there, because OH minus is your base. It doesn't really have an acid for you to give up because, well, remember, if you give up the acid, you can't just have oxygen by itself, right? Because that doesn't exist. Whenever you see OH minus, you can't create a conjugate base for that because OH minus is already the base. All right, I hope that makes I just hope that makes sense in your head, right? OH is the base, so how do you make a base of a base? You can't. All right, so let's look at NH4 plus. What you're going to do is you're going to get rid of that hydrogen. You get rid of that hydrogen, you're going to get NH3, and then you get rid of that charge. All right, because hydrogens are 1, so you lose that charge. H2SO4, when you look at H2SO4, you're going to get rid of that hydrogen, and once again, you're going to get HSO4 minus. I think this is super easy, guys. I mean, the question is not whether it's easy or not. It's whether it's going to stick with you. So practice these because that's what matters. Does it stick? In that last assignment I gave you guys, I'm telling you, 50% of you guys passed it and 50% of you guys failed it. And this is coming just from my pre-AP class. It was a 50-50 ratio. So, you know, these assignments are not easy. I'm going to tell you right now, I am dropping the lowest assignment. So there's that. So that should help you guys kind of have an opportunity to redeem yourself. All right, let's look at this one. You're going to create the conjugate acid. When you're creating the conjugate acids of this, what you're going to be doing is this. You're going to be focusing on that charge. Now, you know the acid must be gaining an H. So if we have OH minus, we can gain an H to offset that negative. That's going to give us H2O. We have a Cl. We're going to offset that by adding an H. That gets rid of the charge, and it gives us hydrochloric acid. We have CO3 2 minus over here. So whenever you see a -2, You got to be careful because we're asking for the conjugate acid of it. The conjugate acid of anything is just adding one hydrogen. So we're going to add in just one hydrogen. Now, if you're really clever, you're going to be like, well, can't you add another hydrogen after this? And the answer is yes. You can add in another hydrogen if you wanted to, and you get H2CO3, no charge, right? But that's what you call a diprotic acid right there. A diprotic acid is when you have more than one hydrogen to get rid of, right? So that's just, that's extra information. It's not at this level, but this, technically, you could add another hydrogen and make another conjugate acid of this guy. All right, so H2O, H2O, once again, can you add another hydrogen to this? And the answer is, yeah, you could, because this is going to be H3O plus. That forms that H plus ion charge, which is hydrogen ion. HS minus, H2S, right? H2PO4, you're going to add another hydrogen, and that's going to be H3PO4. HSO4 minus, add another hydrogen, and you're going to get H2SO4. And I'm going to give you guys some extra credit, because as I'm going through this, I was very tempted to say the chemical names of all of these. So here's some extra credit. If you're watching this, go ahead and just send me a private comment. And what I want you to do, and technically, yes, you could look this up, but don't look it up. I just really want you guys to practice your naming again. So I want you to go and name these, all right? So for instance, H2O, it doesn't have an acid name. H2O doesn't have an acid name. So, but just name it. This is going to be dihydrogen monoxide, right? I want you to give me the acid names. So try that for extra credit. I'll give you guys 10 points. So do them, try them, see if you can get them right. All right. It does involve that you know your polyatomic. So if you don't have your polyatomic chart in front of you and you don't want to Google the answer, just Google up polyatomic ions and go from there. Now I want you guys to create reactions for Bronsted acids and bases. All right, so now you are going to have to create the equations yourself. And if you're creating the equations yourself, you must be able to predict the products. Okay, so now you have no choice but to be able to predict the products. For this case, I did throw everything in water. It does make things easier. So I went ahead and threw everything in water. So HCN plus H2O, right? I threw it in water to see whether it's going to ionize or not. And we're going to ask yourself, so now we don't have this. So we're going to ask yourself, what do you think is going to happen? Well, this can be an acid or base, right? But if you see over here, this is an acid. And if you know he's the acid, he's going to donate this proton. So over here, he's going to be losing this proton. So we're going to get Cn minus. Now, where does this proton go? Well, it's going to this hydrogen over here. So we're going to get Cn minus, and we're going to get H3O plus, right? And I'm really hoping that makes sense, guys. If that makes sense, then you've mastered what I wanted you guys to get out of this. And if this didn't make sense, man, you're just going to have to go back and rewatch this because it is kind of confusing if it's your first time seeing this. But let's look at this one, CH3, CH2, NH2. This is tricky, but remember, ask yourself once again, what can you recognize from this? Yeah, there's tons of hydrogens, but remember, this is a nitrogenous base. That makes him, by default, he's going to be a weak base. And if he's a weak base, we already know we're going to throw it in water, right? So we're going to throw this guy in water. Oh man, I forgot to label these. I'm sorry. This would be your acid. This would be your base. His opposite over here is going to be the conjugate, and his opposite over here is going to be that conjugate over here. All right, so let's go back to this. So we're going to throw it in water, and then we're going to ask yourself, we know that he's the base, so what must the base do on the right side? He must gain, in order to be, he's going to have to gain a hydrogen, so we're going to get we're just adding one hydrogen over here. Now we add this plus charge because now he has a plus overall charge. And where did it gain this hydrogen from? Well, it gained it from this water molecule. This water molecule lost the hydrogen to this guy. Like when you compare this guy to this guy, he must lose a hydrogen molecule. Where did it go? Well, it went to this guy, right? So once you label these, he's the base, he's the acid. We know that he's the base, so his pair over here must be the conjugate acid. Yeah, okay, I just jumped. His pair over here must be the conjugate acid, so his pair must be the conjugate base, right? That makes sense. Try this next one by yourselves. Pause the video, try it, but you get HCO3 minus. Ask yourself, guys, is it an acid or is it a base? And hopefully you know the answer to that. It's going to be I'm just sensing it. I'm sensing all of you guys said acid, all right? So he's the acid. And I'm sorry. Some of you guys might have said base, and so I apologize. He's actually, that was a trick question. He's actually amphoteric, and that's because he has the minus sign there too. So he's got that minus, so he can be an acid or base. So on this one, some of you guys might have had different answers if you tried this by yourself. Hopefully you did both ways. So if I compare the ACO3 to what happened over here, he must gain a hydrogen. So in this case, if he's gaining a hydrogen, he's going to be a base, and this guy must have been the acid. All right, and this guy must have been the acid. And so this makes this the conjugate acid, this makes this the conjugate base. But if you look at the problem on the bottom, and I can't move my arrow down because then I can't see it because that little thing pops up. But in the opposite, I did the opposite on that one. So that pretty much sums up this entire PowerPoint, guys. I know it was a longer video than usual. That's because I had a lot of information to cover on this one. But here's your quick summary. Your Arrhenius acids and base, they will always form H+ or OH ions when dissolved in water. Your Bronsted Lowry acid and bases, these are always going to be donating or accepting a proton, right? If you donate, you're the acid. If you accept, you are the base. There are 7 strong acids that you must know memorize. There are also 8 strong bases that you need to know memorize. But remember, the 8 strong bases come from the B on the periodic table. And the 7 strong acids are ivory and clay. If they're binary, and if they're tertiary, they're going to be 2 or more oxygens than hydrogens. And that's really it, guys. I'm really happy that you stuck with me. I know it was a long presentation, but continue doing you, and have a great rest of the year.